So my computer decided to restart at the right moment. Give me a minute. Till then, I'm the person who's standing between you and lunch. Hi, everyone. I apologize for that in advance. I'm Pavneet Ahluwalia. I'm a senior PM with AKS. I focus on scale and performance. So if you want to ask any questions about that, please find me later. Don't in the middle of the session because people are waiting for their lunch. Cool. So we're going to be talking about building resilient applications at a global scale. So what does that mean, right? Let me start with a few questions from the audience, if you'll oblige me. So how many of you are running or own an AKS cluster that is at scale? Say, greater than 100 nodes. Can we do a show of hands? Okay, few at the back. So most of you are not running at large scale. Cool. Second, how many of you own both the application and the cluster, where you have the responsibility of both the infrastructure? Okay, quite a few people there. Cool. And then I guess the last question is, how many of you have a well-defined resiliency or application SLO that you're actively tracking and optimizing for? Cool. So this is a session for you. You're going to learn some things today. So we're going to walk through today's session through a couple of customer stories. First is Eve. She is an HA-focused, disruption-sensitive customer who wants to ensure that her application is redundant to any kind of infra or zonal failures, right? And the second is Otto, because I built this slide on the flight and I was watching the movie A Man Called Otto. And he is a performance-sensitive person who's running a large-scale application and really wants to optimize for scale and performance, right? Minimize his operational overhead. So let's focus on Eve first and the resiliency story, and then we'll come to the scale part, right? So as we talked about, Eve her main focus is how can I improve the reliability, resiliency of my application? And through that, we are going to talk about both infra resiliency, why you should use availability zones on AKS, what are zone redundant disks, and AKS Fleet Manager, but also the application layer, because it's not enough to do it in the infra side, right? So we're going to talk about topology spreads, service mesh, and some of the other tools at your disposal. So I'm taking a stateless example here to keep things simple. If you have any questions about stateful workloads, feel free to find me later. The case I'm taking here is a pretty straightforward one, hopefully, where she's trying to get to 4 nines availability and optimize for a low RTO. Do we know what an RTO is? Okay. So let's talk about how she started her journey, right? So right at the time of creating her cluster, she realized that there's a feature called availability zones with AKS. And when she dug into it, she found out that it actually greatly improves her resiliency story. Because if you use availability zones with AKS, AKS is taking care of spreading your nodes in your node pool across the selected number of AZs. So in case there is an AZ outage, your application automatically fails over to other AZs and running nodes. So you always have a minimum number of nodes that you want for your application, and your application has redundancies at a node level because they're spread across availability zones. For example, if East US1 went down tomorrow, right, the AZ East US1, and you're running your cluster in East US, if you're using availability zones, then your nodes are spread across 1, 2, and 3. So you still have nodes running in East US 2 and 3, hence your application still has working and running pods there. The second, and probably one of the most important things you need to do in AKS is use standard tier. Now, we recently repurposed the uptime SLA feature into standard tier to better align with the customer value props and features that they look for. What you get with standard tier is higher scalability on the control plane, where we will vertically scale your control plane API server, for example, to respond to load and high scale, as well as auto-scaling some of the other control plane components like etcd. You also get a guaranteed uptime SLA of 99.95% while using standard tier if you're using availability zones with it, right? Without that, you only get 3 nines. So that's a good combination to use standard tier with availability zones. And even if, despite all this, there is an outage on the API server sides, your application is still running, because the only thing that you can't do with API server going down is CRUD operations, but existing pods that are running are not disturbed. So Eve thought, OK, I've enabled standard tier. I've enabled uptime SLA. I'm done, right? No. It's not enough to set your infrastructure to be redundant to zone outages. You also have to make sure that your application and your pods are spread in such a way so that if there's an outage, you're not concentrated all your pods in a single AZ. And that's where topology in Kubernetes comes in. Now, I have a couple of examples here which are showing YAMLs. The first one is using topology spread constraints. Now, what do? They basically control how skewed your pods are going to be when scheduled in your node pool across different topology domains. Topology domain can be one of many things. It could be a region. It could be availability zone. It could be your own defined selectors, where you can use node labels to define topology domains and basically spread your application across them. So when you're doing AZ availability zones, availability zones with AKS, you should use topology spreads to make sure that your pods are also getting spread across those nodes appropriately, and you're not getting too skewed on one particular AZ. Now you spread the pods across AZs, but you have a microservice architecture. You have clients who are calling other services within the same cluster, which are now spread across all these different AZs. So how do you control that traffic? Right? How do you reduce the probability of cross-AZ traffic? Because that can come with additional latency, and soon Azure will actually start charging for cross-AZ traffic as well. And that's where topology-aware hints and topology network configuration comes in, where you can basically hint that the client and the service that is receiving the request are in the same AZ. But this is best effort. This does not guarantee that you won't have cross-AZ traffic within the same cluster. And that's where service mesh comes in. George already talked about Istio add-on for AKS, which allows you to now deploy a service mesh in AKS while reducing your operational overhead to do so. And service mesh really has these built-in controls where you can control how your traffic is spread across AZs, across regions, and across different services in the cluster as well. So the first example we have up there actually shows a logic tree where Eve basically decided that, hey, I'm going to keep my traffic within zone 1, right? Both my two microservices talking are in the same AZ. But in case there's a failure, move to zone 2 within the same region. If that also goes down, then move to second region, zone 3, and that's how she's defining a logic tree of how your failovers happen in terms of cluster networking and traffic, so that you are keeping your priority within the same AZ, reducing your latency and cost. But in case of failovers, you have a well-defined logic of how to fail over to other AZs and regions. Now, we talked about networking. Let's talk about storage as well. Because what Eve realized is, she set up the cross-AZ story well. She set up her topology spreads. But now, they had to handle the logic of replicating the data at an application layer, which is very tough in most application use cases, but specifically with Elasticsearch and some of the legacy SQL-based applications. And that's when they found the ZRS disks feature, which stands for Zone Redundant Disks, which basically allows you to synchronously write to 3 different zones. So you don't have to manage the replication of the data logic at the application layer. It's pushed down to the infrastructure layer. And in case, here again, same example, right? If zone 1 went down, that means the nodes and the attached disks went down. The pods were able to schedule to a different zone because the data was replicated on disk in those zones as well. So that way you have end-to-end full redundancy from application layer to the nodes to the networking and the storage underneath. So that was the infrastructure within the cluster story, right? What if you need cross-region or cross-cluster redundancy? And that's where the Kubernetes Fleet Manager comes in. George talked about it in depth. We're going to do a quick demo about it as well. But the two examples that I want to talk about here is, the first is about how do I control that which regions within a fleet are my applications deployed to. So I have a fleet, I have joined multiple clusters to it, which I'm using as a unit to do my upgrades and to do other fleet management. But you can actually use it for more. You can actually use cluster resource placement to define which regions or other parameters based on labels that I want to restrict my service or deployment to. In this case, it's being restricted to only East US region, so only the member cluster A is getting the service. And the second use case that I want to talk about is L4 load balancing using Fleet. So here you can have multi-cluster service, which is spread across multiple clusters, and you can do L4 load balancing so that A, you can have larger scale, but B, in case of failovers, even if your whole cluster goes down, you still have redundancy in a different cluster and potentially in a different region as well. In this case, it uses the load balancer from one of the member clusters itself and does endpoint manipulation in the backend so that you get multi-cluster service. And I think we are working on L7 load balancing for Fleet as well. So let's jump into the demo. This is a slightly longer demo, so please bear with me. Is it running? Yes, OK. So here I'm creating not me, it's a recorded video, but here we're creating a Fleet Manager resource to which I'm going to add a bunch of clusters as members later. Just selecting a subscription and resource group here, giving a name. We're going to use demo for the whole demo. We're going to call everything demo. And now we're going to add some member clusters to the fleet. To keep it simple, it's member 1, member 2, member 3. Let's hit create. It's going to run its validation and then add those member clusters to your Fleet Manager resource. The deployment is in progress. Let's skip that part to the Fleet Manager resource itself. We're going to go to member clusters to see if our 3 clusters were added properly. And here they are. Right. Now let's switch over to the CLI. And we are going to do some identity and role assignment so that we can run our CLI commands. Now let's pull the kubeconfig for the entire fleet. So now we have a kubeconfig which has the 3 member clusters joined to it so that I can run kubectl commands across the whole fleet. So the kubeconfig equals hub gives it the right context so that I can access all 3 nodes, all 3 clusters, sorry. There they are. Cool. So let's look at the demo application for the first example that we talked about, where we're going to limit the service to a specific region. That's the deployment. We're using a pretty straightforward application here, defining some CPU memory limits, defining the service. We are at port 8080. And then finally, we're using the service export feature here. That basically allows you to export a service from one of the member clusters to the fleet itself. And that's what gives you the ability to run multi-cluster services, because all the configurations are exported at the fleet level. This is the resource placement, cluster resource placement policy that we are defining here. We are creating a namespace called demo. This is at the fleet level. And then within that, we are using cluster affinity, very similar to node affinity, to define, hey, I only want this application demo or namespace demo to be restricted to East US. So only clusters in East US will get that namespace and application. OK, let's apply that. It's created. It's up. Cool. So now we are pulling all the nodes. And as you can see, In member cluster 1, we have the application up and running. Same in member cluster 2. But not in member cluster 3, because that was not in East US. So that's how we used the cluster resource placement to restrict where my application is going. It's very similar to Node Affinity and how that works, but applied at a cluster level. Cool, so now let's configure a multi-cluster service. We're using service import here to basically import the service that we created in the member cluster that we exported to the fleet. Now we're going to use it using the service import feature. We're going to apply it to the entire, okay, I'm going a little fast, to apply it to the entire multi-cluster fleet. Here, we're basically pulling the node IPs which are serving the request, the curl request, right? And there are a bunch of node IDs. You can see that 1.23 was there, 1.24 was there. And now we're double checking, hey, is my service actually being serviced through different clusters? And as you can see, the same IPs are showing up across different clusters. So that's how we're verifying that, yes, the service is indeed across cluster. We have the node IPs which are matching our curl requests, which were spread across different clusters. Cool, and that's the demo. So that's how we use Fleet Manager to do cross-cluster redundancy, both at the service level, but also at controlling which region and how we're going to fail over within that region, across those regions, sorry. The other thing you can do is global load balancing using Traffic Manager or Front Door. Now, this is admittedly quite complicated today, right? And we are working on several features to make this simple through L7 load balancing across cluster, across regions, using the Fleet Manager so that you have a simple story that allows you to do global load balancing across all your clusters, across your entire fleet. So the last part of the story is backups, disaster recovery and backups, right? You can use Azure Backup with AKS to reduce your RTO and really target your RPO goals. You can even use it with Azure load testing to actually test and see, hey, am I meeting my RTO goals? Am I able to get the DR story that I want? Is Azure Backup has a minimum RTO of 4 hours, which may or may not be enough for you, which in that case, you can even use open source tools like Valero, which is what actually Azure Backup is built on top of. And customer can take multiple backups in a day within the same minimum RPO of 4 hours. The backup solution actually uses the same CSI drivers to perform backup and restore. But this requires you to have an AKS cluster higher than 1.21, which is mute at this point. So what Eve realized throughout this whole process, even though you're using the best practices, you still need practice. You still need to load test your application. You still need to do some sort of drills to make sure that is your application code itself able to handle these failures gracefully. For example, AKS does regular AZ down drills or availability zone down drills, where in our canary regions, we will take down a availability zone, and we'll see how our service responds to that. And even though our service stays up, we learned quite a few things from it. For example, we may not have enough quota in our subscription to spin up the whole environment again in a new AZ. So you need to plan for that. And that's where you need to test in advance and not leave it for production. We also realized, for example, that even though AKS resources were zone redundant, the Cosmo DB under the hood that we use was not. So we had to make sure the database was zone redundant as well. So there's really no replacement for load testing in practice. So let's move on to the next story, right? And this is probably my favorite topic because that's the area I work most on. But Otto comes in and he basically says, hey, I have this event-based application that is going to be very spiky. It's going to scale up, scale down frequently across hundreds and thousands of nodes. Can I run it on your clusters, Eve? And I'm going to skip the multi-tenancy security piece a bit, because that's its own problem, and Michael already talked to it. But what we're going to talk about is how to think about AKS limits. We have documented limits, but how do I think about it at a Kubernetes level, which has so many different dimensions? And what are the best practices when I'm trying to optimize for performance and scale? Similarly, auto scenario, we're trying to take a cookie cutter example where his application needs to scale quickly. He has an SLO of end-to-end scaling of less than 4 minutes out of 50 nodes, because that's what he sees the most common scaling step needed to run his application at scale. Sometimes they need to scale beyond 1,000 nodes. And then he's running multiple watches, daemon sets, and CRDs in the cluster, which makes things slightly complicated. So let's get into it. How do we think about scale at Kubernetes? So we asked the upstream folks, and they basically said, you can't. There's no one number that I can give you that defines AKS or Kubernetes scale. Why? Because it's a scale envelope. It's a multi-dimensional body, all of which is being serviced through the same control plane. For example, if I run too many nodes, that does impact how many pods and CRDs and other resources you can run in the cluster. If you're running a lot of CRDs, same. It has a negative impact on how many nodes or how many pods you can run, because it's the same control plane that's servicing the whole clusters and all the dimension that goes with it. For AKS, we have battle tested and validated 5,000 nodes. That is not the default limit, though. The default limit is, for now, 1,000 nodes. If you need to go beyond it, you can create a support ticket and request the upgrade from our side. We support 50,000 pods per cluster. We are currently testing 250,000 with overlay CNI, and hopefully that will become the official limit soon. Services per cluster, well, if it's backed by an LB, you have a limit of 300, and you can run 1,000 nodes per node pool. So for example, if you want to run a 5,000 node cluster, you need a minimum of 5 node pools to be able to run that. And on the back end, we run regular pod churn tests and service creation tests at different scale points using Cluster Loader 2 to test the AKS Kubernetes control plane, which is the same tool that the upstream community uses for its own scale testing and release gating. So let's do a quick demo of 5K nodes. I'm basically just going to show how to create that support ticket and just show a cluster that is running at scale. But before that, there are some prerequisites that you need to enable. This is like an executive summary of all the best practices for scale, where please use standard tier for anything in production or at scale. Use overlay CNI or Azure CNI, depending upon your networking requirements. Use managed NAT for cluster egress. You need to have a large system pool because all your add-ons run there, and they need compute resources, especially at scale. And then you need to run Kubernetes version 1.23, because as part of our testing, we found certain API server issues that we ported upstream and which were captured in 1.23. So the demo. It's working. Cool. So we're just going to go to the support and troubleshooting tab, create a support ticket for a given cluster. Now, these tickets are at a per cluster level. You cannot yet ask for 5,000 node limit at a whole subscription level, but that will change soon. We're working to automating this whole process so that you don't have to go ask us for higher limits. And if you're using standard tier, you can just go scale up to 5,000 node limit. But that's not out there yet, but it will be out soon. So you're asking for a 5K node limit increase for this subscription. You select service, Azure Kubernetes service. You select the cluster for which you want the higher limit. And then finally, you basically ask for the quota limit increase. Now, unlike Azure quota limit increases, these are not instantaneous. There is a lead time for up to a week for us to enable all the features that you need to scale up to 5,000 nodes. So be patient with that for now. But that'll all go away soon, where you don't need to worry about it and you can just scale. Cool. So the ticket is, I'm not going to go through the whole ticketing process, but you basically create the ticket. And that's it. We'll follow up with you. Most probably, I'll reach out to you personally to understand what your use case is and to understand what are the load patterns you're using. And why do we need to have that conversation is what we're going to cover soon. So here's the cluster already created. It has 6 node pools. It has 1.24.5 Kubernetes cluster. I'm just showing that the CIDR ranges for the Docker bridge and the CNI are different. We're running 6 node pools, 5 with 999 nodes each, and the system pool with 5 nodes. I'm not following my own best practice. I'm actually using a 4-core node for the system pool. Please don't use that. Use larger, because stuff like CoreDNS can be very compute heavy at large scale. We're running a job with 10,000 pods, out of which 6,800 are already scaled up. And we're also running a bunch of services in this cluster for good measure. These are internal services behind an ILB. Cool, and that's it. That basically shows one of the test clusters that we actually use for our own 5K load testing. So AutoVendor did that, right? He enabled the 5K, he enabled all the features that go with it. But what they realized was, hey, I still need to optimize for performance. I'm not getting everything I want, right? So there were 3 pieces that he had to look through. First was workload scale patterns. The key takeaway there is not all workloads are made the same. You can have steady state at scale workloads like a microservice, which is always running at 10, 20,000 pods, 5,000 nodes, which is easy for the Kubernetes control plane because there are not a lot of CRUD operations happening at that steady state. Then you have a spiky workload, which is the case with Auto, which needs to scale up, scale down rapidly, which not just scales the application layer, but the underlying nodes and disks and everything that goes with it, right? And then you have a third type, which is bad jobs. We're not going to talk about it here. But those are particularly hairy for Kubernetes control plane. And there's a whole bunch of upstream work happening. There's a new working group spun up just to focus on jobs and bad scenarios. The second problem is API server client behavior. Like I said, Auto was running a bunch of watches, daemon sets, CRDs in the cluster, all of which poll API server in different patterns, and not all of which were following best practices. So we're going to walk through some of those examples and best practices as well. And then lastly, there are a bunch of AKS and Azure features that we've built over time, which really optimize for scale and performance. And you should pull on those levers when you need better performance or higher scalability. So like I said, there are 3 different workloads. You can take a picture of this slide if you want, because we're not going to talk about each of them in detail. But there are 3 different workload types. Each of them have their own considerations, and each of them have their own challenges. So let's focus on Auto's example, right, where he was running a spiky event-based application, right? Now, as I said, this is particularly stressful on the Kubernetes control plane, because when you're spinning up those pods, assuming that you're using cluster autoscaler, which you should, you also need to often spin up a bunch of nodes. Now, if each of those nodes are running daemon sets, those connect to API server and make large list calls to API server. So API server is not just handling the pod creation or the node object creation, but it's also serving all these list and get calls from all the daemon sets and watches that are coming up along with scale. So this kind of workload can be particularly stressful for the control plane. And as he went along, he realized, hey, using KDA with HPA, with cluster autoscalers, removes a lot of my operational overhead. And I can actually optimize my cluster autoscaler profile for my scaling latency SLO. There are multiple levers in the cluster autoscaler profile which control how often does autoscaler look for pending pods, how long does he wait for the pods to be pending before asking for more nodes. And all those drive how quickly is cluster autoscaler asking for new nodes, and how quickly are you able to scale up end to end. So leveraging that is very important when you're trying to target a performance SLO in terms of scaling. And then last, Please keep an eye out for AKS Performance Best Practices doc. That's coming soon. That's going to be one of the biggest things I'm going to be working on post-KubeCon, where we're going to consolidate a lot of the things that we're talking about into a doc for AKS. So let's jump into it, right? The API server problem that I was talking about. So again, we went and asked upstream group and get guidance. How many QPS can a Kube API server support? And there's not a single answer to this question. Why? Because not all API calls are the same. A list call is way more expensive than a get call, and often more expensive than any create call as well. So you really need to think about how many objects, custom objects, whether CRD or watches or daemon sets, are you going to run at scale? And do they really need the latest up-to-date state of all the other objects in the cluster? Or can they leverage API cache? So the first pattern that we see that gets particularly problematic, and that's what Otto faced, was the n-square problem, which is he was running a bunch of daemon sets, right? And now he's running 1,000 nodes. Each daemon set was polling for all the other objects in the Kubernetes cluster. So every time you scale up, let's say he scaled up 100 nodes in one step, all those 100 daemon sets made 100 list calls for all the objects in the cluster to API server, and that impacted API server latency. So here, you need to think about, hey, is the daemon set the best model for me, or should I go use for an operator model where I'm reducing the number of clients making such calls into one or a handful? And second option here is using priority and fairness. Priority and fairness was an upstream feature released a few versions ago, which allows you to throttle certain clients based on the priority that you're defining. That way you ensure that one rogue client is not bottlenecking API server, and you're seeing latency for everything that's happening in the cluster. The second problematic pattern is large list calls. It's not mutually exclusive from the n-square problem, but I want to talk about it a bit more. Here, we saw certain CRDs or third-party and open source tools which were making unbounded list calls to the API server. Hey, give me all the pods. No context, no resource version, no bookmarking, nothing. Give me all the list pods in the cluster. And that's okay at small scale, but when that happens very frequently at large scale, that gets problematic, and you'll start seeing API server latency. That's where you want to consider using informer classes, which were meant to solve this exact problem. You can use a resource version equal to 0 in your call headers, where basically API server will hit the cache rather than going to etcd for all the objects. Now, if you have an application use case where you need the up-to-date state, that is not recommended in that case, but you really need to think about, hey, do I really need the latest state? And last is list in chunks. Use limits and continue parameters to basically paginate your list call response into multiple chunks. That way, each call is less intensive on API server and etcd. And the third pattern is secret watches. Very similar reasons, right? What we saw with the n-square problem and list calls, but what's particularly problematic with watches is not the get calls that it constantly makes. It's the list calls that it makes when it starts the connection with the API server, right? Where it's saying, hey, give me all the secrets, for example, in the cluster, right? And those are where you can see a latency spike. So when you're thinking about your SLO, you need to also think about for which verb do I really care the latency? Do I care about pod creation latency, or do I care about every API response? Right? And that's where you can start optimizing for your particular SLO and your application. How can AKS help you solve for this? So in the troubleshoot and diagnose tool in the Azure portal, we are adding a bunch of detectors, which are looking for common problems that we see in clusters. For example, how big is the etcd size? By giving you that information, we are basically telling you, hey, this cluster is pretty much at its limit. If you need to scale more, maybe you need to go to another cluster. We're also talking about add-on pod kills, where, for example, CodeNS keeps getting killed for some reason, right? You see that as drop packets, DNS connection issues, but you don't know the root cause. That's where you can find that root cause and how to mitigate it. And then soon, we're also going to add API server alerts there, where basically if we see any of these pathological client patterns, we are going to flag it in the troubleshoot and diagnose so that you can look at it and fix your client behavior. Also coming soon, we want to surface API server metrics to our customers, especially the sophisticated customers who really want that information to tune features like priority and fairness on their cluster, right? Because they know what they're doing, and they want the data to enable that tuning. If you have feedback on that feature, please go to that link. The GitHub feature is up there. Please tell us if any particular metric is of interest to you. And the last thing, read docs. Well, if AKS docs are boring, read upstream Kubernetes docs, because they talk about a lot of the same best practices that most people don't follow. Awesome. I heard we do somewhere. Cool. So I'm going to go into a quick demo of the diagnose and troubleshoot portal experience so that you know where to find it and how to use it. So this is an AKS cluster. It's running some nodes. Now, if you go to the diagnose and, first I'm going to talk about, So go to the diagnose and solve problems tab. You can go to known issues, where we've put these known patterns of issues that we see across AKS clusters. It's going to run a few diagnostic tools, diagnostic queries on your cluster. And on that tab, you see the most common issues. Even if it's not applying to your cluster, that's an exhaustive list of what issues you can see. Now, in this particular cluster, we have kills. We are seeing Prometheus, metric server kills. And it's linking to a bunch of documentation, which is telling you how to mitigate these issues. And in some cases, you can't. Some cases, you need to create a support ticket to AKS. But we don't want you to spin your wheels trying to figure out what's happening in my cluster. Use this tool, which gives you immediate actionable insight as to, hey, is there something you can do about this on your own? Here's the doc link. If not, go create a support ticket. This is the etcd one that was just showing, where we are showing the size of the etcd in your cluster. So please leverage this tool. There's a lot of focus in our team to augment more and more detectors into this tool so that you don't have to spin your wheels trying to troubleshoot issues. So, OK, Otto went and fixed all the API server client patterns that they were seeing. Things were better. The API server latency was meeting their SLO. Now, how do I reduce my operational overhead of application scaling and cluster scaling? Because they were using an event-driven pattern, they decided to go with KEDA, which made total sense. Ali already talked about and demoed KEDA, so I won't bore you with redundant information again. But KEDA plus horizontal pod autoscaler really gives you the ability to be hands-off with your application scaling and let AKS and upstream software drive your application scaling for you. You can also optimize your application using some advanced scheduler features to make sure that you have the availability and the performance that you're looking for. For example, please use pod disruption budget to define the minimum number of pods for your critical applications, especially during maintenance events, upgrades that Alvin is going to talk about later. These come very handy. That's how AKS knows how many pods can I bring down in order to do the maintenance event or do upgrades, or in case of failures as well. Then every pod should have resource requests so that scheduler knows can do some heat management on your nodes, right? So it knows how many pods can it schedule. Cluster autoscaler can then use that information, because pods will go into pending faster, can use that information to scale your cluster faster as well. For your resource-intensive application, which was Otto's case, for example, his application needed very high memory, right? Use taints and toleration to isolate those applications into specific nodes, so that because this was a multi-tenanted example, you don't want other applications running on the same nodes which have high compute intensity requirements. because they can bring down the whole node. They can cause an kill on the node, right? And that'll impact other services running in that cluster as well. Use node selectors and node affinity. We already talked about it a bit in the previous section. And then finally, use topology spreads, just a reminder, to spread your application across AZs. Going into the infrastructure scaling piece, right? There are, like I said, there are multiple features that you can use to improve your node scaling. What Otto realized was, hey, my pods are coming up in time, but my nodes are not scaling fast enough, right? Use standard tier, always, right? I'm going to keep repeating it in every slide. Second, using cluster autoscaler with HPA and KDA in this example, you can be hands-off with the node scaling as well, right? And that really reduces your operational load. You really need to have very specific use cases to not use cluster autoscaler with AKS. Otto looked at the cluster autoscaler profile, the link is there, and started running some load tests with Azure Load Tester, which Ali talked about. And through that, he was running some experiments to optimize what are the right configurations for my cluster autoscaler to drive more throughput. Use V4 and V5 VM families with AKS or anywhere in Azure. They have better performance in terms of node provisioning than older generation VMs. Use ARM64 VM SKU for better runtime performance so that you need less. It gives you better cost to performance ratio as compared to other hardwares. Already talked about this. Use larger system pools so that your add-ons have the required compute capacity to run at large scale. Set up container insights, but also very important, use the max surge node pool property in the AZ-AKS node pool create update CLI command. This controls how many additional nodes am I going to provision in one step during upgrades. So you can really speed up your upgrades using max surge property. You can also slow it down because it's a trade-off. The faster you go, the higher chance of failure during upgrades. So you can actually slow it down because if your application is particularly sensitive to disruption, use this lever to pull either way. Going into the networking infrastructure, right? What Otto realized was he was using SLB for ingress, and they started seeing a lot of SNAT port exhaustions. So using managed NAT, you actually don't have to worry about that because it scales higher, scales to a much higher number of outbound connectivity. It is also faster in terms of node scaling because the backend pool management is easier with managed NAT. And for egress, he continued to use SLB. Recently, AKS launched a new type of backend pool for SLB, which is called node IP-based backend pool. Please use that. That enables your node pools to scale faster because the throughput at which we can add and delete nodes from your backend pool of the SLB is higher, hence your node become ready faster. It's currently in preview, but it's going GA soon. So when you're sensitive to your node scaling performance, using managed NAT with SLB for egress, with the node IP-based backend pool, gives you the best performance needed. Now, for east-west traffic management, he really had two choices because of his scale. It was either Azure CNI with dynamic IP allocation or overlay CNI. And what he realized was, with overlay CNI, he was not just able to run at much larger scale because he didn't have to worry about VNet IPs, but also the throughput was higher. Both the TCP throughput at a host level, but at the host level, but also at pod to service communication as well. So they selected overlay CNI for their use case. Now, if you have a use case where you need services or pods to talk to other pods across clusters, you can't use overlay CNI right now. You'll have to use Azure CNI because it gets the external routable IP address per pod. So from networking perspective, they went with overlay CNI for Cilium with Cilium data plane, and they use managed NAT for egress or ingress. And with Cilium, they actually realized that they were able to scale horizontally with the cluster much better and use more finer-grained network policies as compared to NPM as well. So last but not the least, let's go back to the storage, right? Because, hey, if I'm not able to scale my disks, my storage underlying my VMs, I'm still bottlenecked by either runtime IP, runtime IO exhaustion, or just horizontally scaling it. So there were a bunch of best practices that we talked about in our docs that help Auto. First, if you're running a stateless workload, please use ephemeral OS disks. They're free, and they come with much higher throughput as compared to managed disks. Use CSI volumes and storage classes. Use Azure CSI driver, because we make a bunch of optimizations around how it calls Azure APIs. So you'll see a lower throttling, higher performance in terms of disk attach. Now, there are some customers who use their own CSI driver. We don't really recommend it unless you have a very specific need for it. Use zone redundant volumes. We already talked about it in a few slides ago. Understand your workloads requirement. So if you're using managed disks, right, you can use performance tiers to dial up or dial down on the throughput and IOPS that you're getting. So if you're running a very large VM, you set the right CPU memory limits for your pod, but you were not using the right disk performance tier, you're starving your application of read-write IOPS to the disk, right? And you're still going to see worse performance than you should. So you leverage performance tiers to make sure that you're getting the right throughput for your application to write to the disk. Use stateful and dynamic persistent volumes, configure data protection. Those are all best practices that you should follow when using managed disks with AKS. You can take a picture of this slide. It's a plug, basically, where we're talking about some of the features that are coming soon around block storage and file storage that you can look into. Sorry, still taking pictures. Go ahead. So the bring your own keys with ephemeral OS that Michael talked about really removes another blocker that some customers have to use ephemeral OS, because now you can bring your own keys and do encryption for ephemeral disks as well. So even Auto set up their clusters. Auto was able to scale and meet his performance SLO. Eve was able to get cross-zone, cross-region redundancy and get the high availability in 4 nines as well. And these are the key takeaways from their experience. Start with your application SLO. Define it, test for it, because without it, there are so many knobs that in Kubernetes that you can end up spending time where you don't need to. Think about both the application and the infrastructure layer, both when it comes to resiliency, but also when it comes to performance. It's not enough to just optimize one. Load test, adjust, and then test again for good measure. Because there's no replacement of a real load test. I worked with several customers who are running large-scale, performance-sensitive applications. And until you really load test, you don't know what issues you're going to run into. For example, in one example, they were running open source third-party Prometheus that was just bombarding API server, right? And until you test at scale, you wouldn't find that issue. Use AKS managed add-ons, features, and best practices, because we try to test them at scale. They remove a lot of operational overhead from you, and really they're optimized for both scale, performance, and resiliency. Fifth, not all workloads are the same in Kubernetes. There's a big effort, for example, I talked about this a bit, in upstream community to improve jobs performance in Kubernetes. If any of you run job type deployments in their clusters, cool, few people, you know it's a pain, right? Especially from, he's nodding, especially from performance perspective, right? And it's a multifaceted problem that both the upstream and AKS is working on solving. So when you're defining an application SLO, it's important to understand how does that impact the cluster, and there are different levers to pull and optimize for it. And then last point, if you don't have an SLO, you cannot optimize for it. And you're just waving your hands in the air and hoping everything works. That's it. That's end of the talk. Please hit me up on LinkedIn if you have any questions, or find me here afterwards to talk about anything perf scale or reliability. Thank you.